Sedimentary rocks are grouped into two categories, detrital and non-detrital. We're going to begin with the higher energy rocks, and you can't get much higher energy and closer to the source than breccias. Breccias are angular, they're usually pebbles and gravels, and go all the way down to a matrix of clays or sands. This means that the energy is very, very high, and it is short-lived, or it's constrained to a very short area from the source, from the provenance. So with very high energy, we can transport large grains and small grains. We can transport it all. And because it's short-lived, it means all of it still stays together. If this wasn't short-lived, then we would be able to separate out the grain sizes. Environments in which we find these are things like rock falls, alluvial fans, so the debris aprons that come out from mountain valleys, faults where the rocks are being broken and jumbled and they can't go anywhere, phreatic eruptions. Yeah, I know that these are igneous. However, the cause is the same. You're breaking it up into breccia fragments, and then it all gets deposited together. And then glacial talus does this too. This is the Black Hawk landslide 17,000 years ago, where chunks of limestone released from the scarp. The debris, blocks maybe the size of Volkswagens and SUVs, as they started to smash into each other to create grains of smaller and smaller sizes, but all still angular. The air, the oxygen that got trapped underneath it, allowed it to float and to continue to accelerate up to about a speed of 250 miles an hour, which is why this thing was able to travel for so long and even hop over this ridge line here, which is now partially buried. Here it exposes a bit. Conglomerates, still pretty high energy, but as you can tell from the matrix, it's got to have some low in there. So let's figure out how that happens. We usually find these downstream from breccias. So it's much like a breccia, except the angles have been knocked off, maybe from physical weathering, maybe from chemical weathering. Still poorly sorted. The energy therefore must be high and low. With the energy to transport these larger clasts along the bed, the stream must be carrying all sorts of sand and mud as well. And if these larger pebbles, gravel and pebbles and coarser sands, are tumbling along, and they happen to settle on muds and sands, that mud and sand will be trapped in that interstitial space. Also, if there's still free, open pores, free interstitial space, and clay and mud increases and is traveling along the bed and becomes the bed load, it can find itself packed and falling into these, in between these grains in this interstitial space, and then it's pretty much trapped. It's high in the stream channel, but it's very low in between the rocks. Close-up microscopic view of a conglomerate yields something like this. A very thin section of rock is sliced on a microscope slide, and then we look at it underneath so that the light can come through the crystals, through the minerals. When we cross the poles, so we control the light in its direction and it scatters through these minerals, we see quartz grains, which are this clear, kind of solid gray or solid white or solid light gray. And then we see things that are striped. The striped is feldspar. This is the twinning. So we talked about in oligoclase, the mineral oligoclase, and how you can see the solution bands. And these bands are things of higher calcium and then higher concentrations of sodium, and they're also angled differently. This is the twinning process, and this is why we see these checkerboard patterns even. The crystals, or seemingly crystals, these clasts, these grains that have many different textures to them and many different colors or even appear speckled, these are not single minerals. These are multiple minerals. In fact, I would venture to say this actually looks like clay. That's biotite right there. Here's another biotite and another biotite. Biotites usually look yellow. And this would probably be something of a standard clastic sedimentary clay, which we find conglomerates forming in braided streams and meandering river bottoms. The Toklat River flows through Denali National Park. Braided streams occur because the amount of erosion and the input of grains into the basin exceeds and is happening faster than erosion can carry it away. Taking a look at these valley walls, we have bedrock over here and bedrock here and a bunch of rounded to sub-rounded grains in here. When they cored the toclatin, they drilled down to see where they would finally find bedrock. They discovered they had to drill about 200 feet at the most. Oftentimes, yeah, only about 100 feet down, but still, that's 100 feet of sediment, of these grains accumulating, filling this basin up because glaciation and rain waters are carrying these mountains down into the valley so quickly, just choking the basin, forcing a braided stream. Love braided streams. Quartz sandstone is, well, it's made of quartz and it's made of sand. So the sorting is well to very well. The grains are usually sub-rounded. They can be rounded, fully rounded, but that depends on the amount of time that they were eroded. They form at distance to the source where the energy was not constrained. The energy was able to separate out all the grains, where the breccias and gravels were way upstream, and then it was able to isolate the sand, take the mud and the silt further away. The energy, therefore, we say is moderate, and it is sustained. So if the energy is sustained all the time, it's going to have one type of grain, and it's going to be very well sorted. It's the second most common rock because it forms at beaches and deserts. It also happens to be that quartz and sand kind of go together because quartz can't really be pulverized anything less than a sand-sized particle, which is also why when people think of quartz, they think of sand, and when they think of sand, they think of quartz. Ta-da! If we looked at a thin section of quartz, this is what we would find. Where the whites, grays, the light grays, the dark grays, the blue grays, all of that is quartz. The blacks in this image are metals. Arcosic sandstone. At first glimpse, you're like, it's pink! Well, yeah, it is pink, but it also has subangular to rounded grains in here. Looking at it just under plain light, it all looks the same except for a few dingy, spotty locations. Crossing the poles yield lots of quartz grains that are sub-rounded to subangular, and then feldspars. So arcosic sandstone has to be easily weathered. It also means that it has to be near source because feldspars weather very quickly on the surface of the earth. The sorting is moderate to poor, which also suggests near source. And it also suggests that the energy can be sporadic and forms and alluvial fans to make things like Garden of the Gods, which is the fountain formation. If ever you've been at the Garden of the Gods, or let's just say you've been at Red Rocks and you've been totally bored because the concert there just isn't really jiving you, and you've taken a look at those pink, gorgeous rocks, you'd be able to find horizons, so layers or planes in the rock, where suddenly the size of the grains just seems to be much larger than the surrounding. This suggests for sporadic outwash, sporadic energy change, where the energy change just suddenly spikes, carries in the large grains, and then the energy dies, and you have a return to the normal grain size, which is something like sands, whether they're fine sands to coarse sands, so very coarse, meaning very large sands. And from this, every once in a while, you still see these horizons again and again and again. This fountain formation formed during the period of the ancestral Rockies about 300 million years ago. Yes, 300 million years ago, we had a whole other chain of Rocky Mountains. The Rocky Mountain chain we have now is only 70 million years old, but 300 million years ago, we had a much larger Rocky Mountain chain, and as this was eroding away, these granites were eroding away, they made these outwash plains, these giant alluvial fans, these aprons that spread out from a mountain valley, and it made the fountain formation, Red Rocks and Garden of the Gods. Gray wax. So now we're getting into the greater depth where underneath the water. Gray wax have a moderate to well-sorted nature to them. They have this thing called graded bedding. It's graded from large to small clasts. We can see this here in this turbidite series, in this gray wax series, because we go from gray wax sandstone all the way up to quartz siltstone. Now, gray wax has a whole lot of mud in it. The mud is what is binding the crystals together. The mud is oftentimes coming from feldspars. You can see the feldspars in this twinning or cross-hatched pattern. You can also get a little bit of it in this grain. And you can also see that the quartz is kind of angular. Whether it's pebbles, whether it's gravels, there's a whole lot of mud, a whole lot of clay. These do reflect turbidite sequences where there's a high energy release, so the energy is released much like a breccia, and that creates the angular, subangular nature of the grains, and then as soon as it starts to slow, the grains trap the clay cement matrix between them, which is where they get the clay from. Then they settle, they stop, and then you get the graded bedding. Here's a nice little model of a turbidity current where you have a release, usually of a submarine canyon wall, it breaks off, or say you have a mudslide that hits into a lake, and immediately the material starts to flow, and you have your larger grains at the base. They settle out first and they stop, but the finer ones still take a while because they're still kicking up in this turbid water, which is why we call it a turbidity current. Let's take a look at the link. That's my intro music. The grain size here is just regular sand. It tumbles looking like mud because it's suspended in water. And this guy just realizes suddenly, holy crap, I thought this was small. And he's about to get engulfed by the mud. So what he saw was the forefront, what we call the toe. And everybody's high-fiving because they're all still alive, because they're in the wrong place at the wrong time. And these are second and third pulses. After each pulse, it's going to re-kick up any of the fines that are trying to settle. But these pulses, you'd still be able to see in the gray whack. And we'll take a look at more of these. Fantastic. Mud-like rocks. The most common sedimentary rock on this planet. Why? Because what we don't have a shortage of is quiet water. The oceans, lakes, swamps, Everglades, quieted water. They are well sorted because before something can become quiet water, you go through every single energy there is, and all other grains drop out. From the settling laws, slightly currented, turbid, or wave action water keeps silt in circulation. Mudstone is clay, except it's massive. It's not like shale, it's not like fissile. The only difference between mudstone and shale is fissile, meaning it splits along fine bedding planes. Many people think that these are representing a different layer, a different time period, a different surge of mud. There's not a whole lot to sustain that. I mean, there is in some locations seasonal layers like the varves that we talked about that occur at the bottoms of lakes, so seasonal clay layers changing from the spring thaw to the winter dormancy period, but really we need more data. The mudstone is the massive. So this, a lot of scientists kind of agree that this is probably one quick event of mud falling because there are no laminations. And this is the fissile shale that's coming off in sheets that some say could possibly be individual events of mud drifting in. However, through lithification, through the compaction after being buried, there is a lot that could possibly happen to create this fissile behavior. This is what shale or mudstone looks like up close. These are clay minerals. They are reorganized orthoclase feldspar through hydrolysis and through biochemical means. They were not regrown, they were just reorganized. And so they're small, equine flaky, subangular grains. And in oil shale, I want to talk about this because a lot of people think that energy is going to be saved by getting oil out of oil shale. Well, how? So oil shale is weakly fissile because of the microscopic oil inside called kerogen. Kerogen is this stuff. So this microscopic slide might be about 1 inch by 1.5 inches, and this would be a smear of kerogen. It's a very waxy oil. It's like paraffin wax. We can't just remove kerogen and then shove it in our cars and run our cars. That's just not going to happen. Instead, there's a long process where we have to pressurize it under heat. It takes a lot of energy to turn it into oil. It almost takes as much energy to turn into oil as it gives us. So it's really not that viable as an energy source.